This is the first video for Chapter 5, which covers integration. We have been talking about derivatives for a long time. It's time to get to the third important construct of calculus, the integral. To do that, we're going to start by learning how to approximate the area under a curve and above the x-axis. We're going to use what are called Riemann sums to do this, named for Bernhard Riemann, a German mathematician who first formulated them. In the last section, we studied antiderivatives. Remember, the antiderivative was the process of undoing the derivative. We are going to connect the idea of the antiderivative function with finding the area under the curve. That won't happen until we cover the fundamental theorem of calculus, which occurs in section 3. In this section, we're going to focus instead on approximating area. We're going to have our functions be non-negative so that they're entirely above the independent axis over some closed interval. And then we're going to look at methods of approximating the area under the curve and above the independent axis. This is often called a definite integral, and we'll learn more about the definite integral in the next section. For now, we start with approximations called Riemann sums. Let's look at the learning objectives for this particular section. In this section, we're going to use what's called sigma or summation notation to calculate sums and powers of integers. This will make our work in dealing with Riemann sums easier. Then we'll use the sum of rectangular areas to approximate the area under a curve. In other words, we're going to approximate the area below some curve and above the independent axis by dividing it into, well, rectangles, finding the area of the rectangles and adding them together. That's basically what a Riemann sum does. We'll use these sums to approximate the area. Let's now talk a little bit about area and the process of approximating it. This has been studied for millennia. The Chinese studied this, well, 5000 BC or before. These methods have been around for a long time. Let me share my screen with you, and I'll share one of the methods called by exhaustion in order to see how we might calculate or approximate the area inside of some particular shape. The method of exhaustion was known to the Chinese, as I said, in 5000 before the Common Era, and probably before that as well. Archimedes used it as well around the turn of the Common Era as a process to approximate the area of some particular shape, such as a circle. What happens is you take this shape, in this case a circle, and you fill it with geometric shapes whose area you can compute, such as squares, the blue one you see here, or triangles, such as the one you see in red, and again in green. By dividing an irregular shape into shapes you know how to compute the area for, rectangles, triangles, squares, you can actually find a good approximation for the area of that irregular shape. This is how the area of a circle was computed for a long time. In this section, we're going to develop some better techniques to approximate the area between a curve defined by a function f of x and the independent axis, which is usually x-axis for us, but over a closed and bounded interval on the x-axis from x equal a to x equal b. Like Archimedes, we're also going to approximate the area using known shapes for which we can calculate the area directly. we'll be using rectangles. By using rectangles with smaller and smaller widths, we get closer and closer approximations to the area. But in order to go from A to B every time, if the widths get smaller, then I have to have more rectangles. And if I take the limit as the widths of all the rectangles go to 0, or alternatively, the number of rectangles goes to infinity, I can actually calculate the exact area under the curve. We're going to start by looking at functions that are both continuous over the interval and non-negative. We'll relax these rules in the next section. But for now, we're going to focus on ones that meet these conditions. Let's take a look at some examples of how we can use rectangles to approximate the area under a curve. You can see in both the first and the second picture that the rectangles are approximating the shape of the curve, the function f of x. However, in the second picture, there are far more rectangles. There are 32 compared to 8 in the first one. Notice that the rectangles fit the shape of the curve much better when there are more rectangles. That means that this approximation will be a better approximation than the one with only 8 rectangles. We can clearly see in the first rectangle that there is a section of area that is under the curve that is not inside the rectangle. And this is an error in approximating the area under the function. When we talk about the area under the function, we're talking about the region that I'm shading now, which would be all of this area right up to the value of the function and going straight across. The exact area is given by the shaded yellow region, but we can use more and more rectangles to approximate that exact area. Notice that as the number of rectangles increases over the fixed interval from A to B, the width of each rectangle decreases. Let's talk about what's called summation notation. We use summation notation because, frankly, trying to find the area of 32 rectangles is a lot of busy work. So we use sigma notation to help us, well, speed up that work. Sigma is a Greek letter, as we saw in the last section when we studied the indefinite integral, and it represents, in this case, a sum. S for sigma, S for sum. We use sigma notation or summation notation to add together long strings of numbers, such as the area of the 32 rectangles in the previous picture. This shorthand notation for sums is called summation notation or sigma notation. We're going to use the Greek uppercase letter sigma, which you can see here, to represent these long sums of numbers. For example, if you want to sum all the integers from 1 to 20, you could write 1 plus 2 plus 3 all the way up to plus 20. Or you could use a dot, dot, dot in the middle to represent it. We can also represent this with sigma or summation notation. You'll see here the Greek letter for uppercase sigma, and you'll see an n equal 1 to 20 of n. The n that's on the inside is called the summand, the thing that's being added together. The n that's underneath the sigma symbol is called the index, indicating which letter or variable will be used inside the summand. You can start at any value you want, and you can stop at any value you want. It is customary, however, to generally start at either 0 or 1. And there are good reasons for that, which we'll discover in calculus 2. Most of ours will start at 1, although sometimes we may start at 0. When we start here, this means take the number 1 and add it to, iterate one time, let n be 2, 2, iterate again, let n be 3, all the way up to 20. In other words, the value of the index is changing by 1 each time. We're substituting it into the summand and adding the results of all of those together. We stop when we reach the value of the upper number. Let's now formalize these definitions. The index of summation is the one that is found below the symbol, indicating what the variable is inside the summand. The summand is the part behind the sigma symbol. In this case here, the summand is n. And in fact, n is also the index. As we'll see in calculus 2, it is possible to have more than one variable inside the summand, but the sum only depends on the index variable, not any other variable. We call the one that appears here the lower limit of summation. This one represents the first value for the index as we iterate. The 20 represents the upper limit of summation, the last value we substitute into the summand before we add all the results together. Let's talk a little bit about the process of the sigma symbol. Again, we start with the lower limit of summation substituted in place of the index in the summand. We compute that value, then we iterate and allow the index to change to the next integer value. And we substitute that into the summand, find that value, and add it to the previous value. And we iterate again and let the index take on the next integer value. We repeat the process until we reach the upper limit of summation. Each time, we add the value to what we had before. It is possible for the index to be increased by something other than 1, though we will not use these. It is possible to increase it, say, by 2s. So if you start at n equal 1 and you go to 5, first n would be 1, and then 3, and then 5. In our case, we'll always go by 1s. Now, when you do this, you're going to make sure that the index is used only to keep track of the terms to be added. It's counting for you how many times you substitute a value into the summand, and then you're going to sum all those values together. It doesn't factor into the calculation unless it appears in the expression to the right of the symbol, which is the summand. The index is considered a sort of dummy variable. It helps us to compute the sum, but it doesn't show up in the final answer, which is, typically speaking, some real value. Let's consider this example here. The summation from n equal 2 to 5 of the summand 2n plus 1. Notice that the index is n, indicated by having it as the variable below the sigma, and it does appear inside the summand. When we start this one, our first value for the index is the lower limit of summation, which is 2. So we're going to take the 2 and substitute it in place of n in the summand. That gives us the value of 5. We set the 5 aside and we iterate once. meaning now increase the index by 1 to 3. We let n be 3 and recompute the summand, this time obtaining 7, which we add to the 5 we got the first time. Then we iterate again. Next time, we allow n to be 4, substitute it in the summand to get 9, and add the 9 to the 5 and 7 that we got on the first and second iteration. Finally, we reach the value of the upper limit of summation, 5. We again substitute the 5 in place of the index in the summand and compute the value, which is 11. Adding to the previous sums, we get 5 plus 7 plus 9 plus 11, which is 32. In other words, the sum from n equal 2 to 5 of 2n plus 1 is the number 32. Notice the index does not appear in the final value. This is why we call it a dummy variable. Let's go ahead and write the sigma notation and evaluate the sum of terms 2 to the n for n between 3 and 6. We are going to always iterate by 1, so let's go ahead and figure out what index to use and what the lower and upper limits of summation must be. And then we can compute what the summand is. That's my best Greek letter, sigma. Since it said for n equal, we can stick with n. We want to start at 3, and we want to stop when we reach 6. It is common to use n or k, sometimes m or l, even j, for the index of summation. We used to use I all the time, but as we've learned more and done more with the imaginary number I, that got to be a little problematic. So we've gotten away from using I. The most common variables to use for the index are n and k. Now that we have the lower limit of summation and the upper limit of summation, we need the expression for what it is that we're going to be substituting the index into, the summand. The summand, in this case, is 2 to the n. What does this mean for us to do? We're going to start at the lower limit of summation, which is 3. We're going to substitute that into the index in the summand. Then we're going to iterate. We're going to substitute 4 the next time into that place and add it to what we got on the first iteration. Then we're going to substitute 5 and add that to what we got on the first and second iteration. Finally, we reach the upper limit of summation, which we do substitute in, and we'll evaluate all of these and add them together. When we do this, we end up with the value of 8 plus 16 plus 32 plus 64, which gives us a sum of 120. In other words, we can shorten our summation by computing this sigma or summation notation. It's easy to compute a summation notation using technology, which we'll use when we have a lot to compute. Let's now look at some of the properties for sigma notation. We're going to allow a sub 1, a sub 2, all the way up to a sub n, and b sub 1, b sub 2, b sub n represent 2 sequences of terms. In other words, an ordered list. There's a first, a second, a third, and so on. We're going to let c be some constant real value. Then the following properties will hold as long as we use some positive integer for n, and in fact, it also works for n equals 0. And we're going to take m to be less than equal to n and greater than equal to 1. Note that the first formula does require that the index start at 1. There are some formulas that require starting at 1. In that case, we'll have to learn how to convert if the formal one actually starts at 3. We'll have to convert it into one that starts at 1 so we can use the formula. In the case of the summation from k equal 1 to n of some constant, we just multiply the constant by the upper limit of summation. Because there's no index in the summand, there's no place to sub in, which simply means that what we're doing is we're adding c to itself n number of times. And because of that, we get n times c. For example, the summation from 1 to 5 of the constant 7 would give us 5 times 7, or 35. The second property applies to having a constant multiplied by some expression, possibly involving the index. If I take the sum from k equal 1 to n of the constant times the expression with the index, the constant can actually be factored out. If you think of what we did here, the constant is in every term, it's a greatest common factor, and it can be factored out and then multiplied by the sum of the expression a sub k. For example, if we look at the sum from n equal 1 to 42 of 6 times n squared, the 6 will be multiplied by every term 42 times. So we can factor the 6 out and then compute the summation from n equal 1 to 42 of n squared and multiply the result by 6. The next property that we have is that the sum of the summation of the sum of two expressions involving the index, or the difference, is represented by the sum or difference of two separate summations. When we get into calculus 2, you need to be careful, because in calculus 2, we are going to allow these summations to go to infinity. This particular property only applies when n is a finite number. This says that I can split up terms in the expression involving the summand and the index, so that the sum from 1 to 12 of the summand 3k squared plus 2k can be rewritten as the sum from k equal 1 to 12 of 3k squared plus the sum from 1 to 12 of 2k. And again, I could factor out the 3 and the 2. Let's now take a look at the last property for summation. This property is the one we're going to exploit when we need the summation to start at 1. There are formulas which require that the summations start at 1 and go to a finite value. We've already seen property 1 requires this. We're about to see several more. When we have something that does not start at 1, we can use this property to rewrite it. This says that if I have the sum from 1 to n, let's say 15, of the expression a sub k in the summand, then I can split it to go from 1 to m, where m is less than 15, and add to that the sum starting at the next number and ending at 15. So for example, if I want to look at the sum from 1 to 22 of the expression 3k minus 12, which yes, I could split it up, I can instead write this as this, did I say 12? No, I think I said it right. The sum from 1 to 12 of 3k minus 12 plus the sum from 13 to 22. Again, if I want to go from 1 to 22, I can stop at any number between 1 and 22 and split it into two summations. I could go from 1 to 9 and then from 9 to or 10 to 22. You wouldn't want to repeat 9, it'd get counted twice. Now, how does this help us to rewrite a summation starting at 1? If I start with the one that starts at, say, 13, and I need something that starts at 1, you got it, you're going to subtract this sum from that one. And you have the difference of two sums, which both start at 1, so you can apply the formula. Let's now look at some more rules and sums and powers of integers. If k represents an integer, and it would because it's the index and we're iterating by 1, then the sum from k equal 1 to n, a finite number, of just the index, which will give us 1 plus 2 plus 3 up to whatever n is, like our example of adding all the digits from 1 to 20. You can find that value instead of actually adding them together by computing the formula, the upper index of summation, upper limit, times 1 greater than the upper limit of summation, and dividing by 2. So for example, if I want the sum from n equal 1 to 7 of n, and it is okay to use n for the index, I would compute 7 times 7 plus 1, which is 8, divided by 2, which gives me 28. Note that for this particular rule, it must start at 1 for the lower index of summation. This is a formula that requires the lower limit of summation to be 1. The next two formulas also require that the lower limit of summation start at 1. We have a formula for the sum from k equal 1 to n of k squared. Recall that we did one of these earlier when we did 2 to a power. In this case, we have 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to the upper limit of summation squared. Instead of actually computing each summand and adding them together, I can use the formula n times n plus 1 times 2n plus 1, all divided by 6. The last formula that I'm going to give you is the sum of the index cubed. If I have the sum from k equal 1 to a finite number of the index cubed, then I can compute that without having to find any of the individual summands by computing the upper limit of summation squared times the upper limit of summation plus 1 squared, all divided by 4. If we have to compute the area of 32 rectangles, these formulas can help us simplify that work and make it go much faster than actually computing the area of all 32 rectangles. In this example, we go from 1 to 10 of n cubed. This gives us the upper limit of summation 10 squared, 1 plus that, or 11 squared, and we divide it all by 4 to get 3025. Here's the method that we use in order to rewrite something that does not start at 1 to something that does start at 1. We're using the property that we had up above, property 4, and we're solving for the sum where the lower limit of summation is not 1. We get this by taking the sum from k equal 1 to n, the upper limit of summation, and subtracting the limit from 1 to m, which is 1 less than the number that we see here. Let me write down an example of this. Let's suppose I want to find the sum from k equals 12 to 50. That doesn't look much like a 5. There we go. Of a sub k. I start by taking the full 1 from 1 to 50, and then I subtract off the first 11. In other words, if I take all 50 and then I subtract off the first 11, then I am in essence starting at 12 and going to 50. Now that these two are written starting at 1, I can use the formulas for k, k squared, and k cubed. I don't require my students to memorize these formulas, although they are very handy. If you need them on one of my exams, I'll provide them. Let's use these to write the sum of values of the sum n 4 plus 3k for k between 1 and 100 using sigma notation, and then evaluate it. In this case, when we write it down, we're going to have the sum from k equal 1 to 100 of the sum n 4 plus 3k. Now we want to use the properties and the rules for sigma and summation notation to simplify this. Because I have a sum, I can split this into the sum of two different summations, both from 1 to 100. Then I can use the rule that allows me to pull out a constant to rewrite the second one as the sum from k equal 1 to 100 of k, then multiplied by 3. Now I can use the rules that we had previously to rewrite this. Remember, it is required that if the sum starts at 1 and you just have a constant for the sum end, then that is the upper limit of summation times the sum end. And that would give us 100 times 4 for the value of the first sum. And notice I got that without adding 100 numbers together. The second one has a formula, which I don't expect you to memorize, so you'll see it here down below. When you start at 1 and you go to a finite number, the sum of the index is given by the index times 1 plus the index divided by 2. In this case, we'll have 3 times 100 times 101, all divided by 2. And then I can simply simplify these results and come up with the solution much faster. And I am hunting for my values. This would give me 15,150. You can use a scientific calculator to find it, which gives me the final value, 15,550. It's much easier to compute that using the rules and properties of sigma notation. Go ahead and pause the video and work out example 3, then turn the video back on so that we can compare. So let's compare. When we look at this particular summation, we see that we have a sum in the sum end. We can split it into the sum of 2k and the sum of 1, both from k equal 1 to 20. Then we can pull the constant off of the 2k to get 2 times the sum of k. We know that when the sum end is a constant and we start with a lower limit of summation of 1, we can multiply the upper limit of summation by the constant, which gives us 20 times 1, or 20. We use the formula for the sum of the index in order to compute the first summation. And when we're done, we get 440. Let's now look at example 4, where we want to evaluate using a difference of sums. We want to evaluate the sum of k from k equal 5 to 10. In order to compute that sum, we're going to have to split it into the difference of two other summations. The first one must be larger and go further than our original, and it must start at 1. So we have the sum from 1 to 10. However, I really don't want the first 4, so I subtract the sum from 1 to 4 of k. Now that you have the formula down, go ahead and pause the video to apply the formula and turn it back on so we can compare. Let's see now what you have. If you look at the representations, we've used the formula for the summation of the index by itself in both of the summations on the right. This gives us 10 times 11 for the larger summation divided by 2, and 4 times 5 divided by 2 for the smaller summation, taking off the terms that we didn't want. Then I subtract the 2 to get the sum of the one I really was interested in, the sum of the index from 5 to 10. This is how we can use the formulas even when the index does not start at 1. This will become very important as well in Calculus 2, where we use series a lot, and series are summations. Let's look at one more example, example 5. In example 5, you can see that we have the sum from 1 to 20 of the constant 100 times k squared minus 5k plus 1, all in parentheses. We can take the 100 out, and we can split it into the sum and difference of different sums. But if you do so, remember, the 100 is being multiplied by all 3 terms. So it must be a constant at the beginning of all 3 sums. We do have a term that is k squared, so we'll need to apply that formula. And we have one that is just k, so we'll need that formula as well. Pause the video now to work this one out. So let's see how you did. Aren't these fun? All right, maybe you don't think they're fun, but I do. When we're looking at this, remember the 100 has to be distributed, so it should show up as a constant on each of the sums when you split them apart. This gives me the sum of k squared, the sum of 5k, and the sum of 1. The k squared is a formula that I know how to apply. I take the upper limit of summation, 20, and I multiply it by itself plus 1, 21, double itself plus 1, 41, and divide the result by 6. Unfortunately, it's a bit more time in order to prove these formulas, and probably beyond what we would want to handle at this point. You'll just have to take them on faith. For the second summation, notice that I still had a constant multiplied by the index k. I can take that constant out as well, giving me 100 times 5 on the outside, and then the summation of the index from 1 to 20. That one is going to give me the upper limit of summation times itself plus 1 divided by 2, and then multiplied by the constant on the outside. The last summation ended up being the sum from 1 to 20 of 1, which gives me the upper limit of summation 20 times the 1, and then multiplied by the constant 100 on the outside. Doing a little bit of arithmetic or grabbing a scientific calculator will give you the result of 184,000. Much, much faster and simpler than trying to compute this value 20 times and adding it together. We now want to take what we've learned about sigma and summation notation and apply it to the problem that we started with. Namely, if we have a function that is continuous over a closed interval from A to B, and it's non-negative, not going below the independent axis, how can we approximate the area under that curve between the independent variable equal to A and the independent variable equal to B? Normally, x equal A and x equal B. We're going to use what we've learned about sigma notation to make adding up the area of these rectangles simpler. The ones that I'll work here in the video are going to be relatively small because I'm doing them by hand. But you can expect on the homework that they may ask you to do it for 20 rectangles or more. For that, you'll definitely want to engage some technology and use the formulas from the properties and rules of summation. We're going to start by letting our function f be continuous and non-negative and defined on the closed interval from A to B. We want to approximate the area bounded by the function above, the x-axis below, the line x equal A on the left, and the line x equal B on the right. When we look at the image, it looks like this. You can see the vertical line on the left, x equal A, the vertical line on the right, x equal B, the x-axis, which is y equals 0, and the top is the function. We want the shaded area, which is the area underneath here. This is one of the two problems that motivated the development of calculus, which caused science and engineering and physics and medicine and biology and economics to simply explode. There were so many more things they could do and learn and study and explore once calculus was created. When we look at this, we're going to start by subdividing the interval from A to B. We're going to divide it into small sections. If we take these, we can make vertical lines that subdivide the interval. And by subdivide the interval, I mean I'm taking little regions down here. The widths of these do not have to be the same, but it does make our calculations easier when they are. So most of the time, we'll make them the same. In fact, it's not until you get into a real analysis class as a junior mathematics major that you would look at not allowing them to be the same. In this case, we can call these a partition of the interval A to B. We often let the one on the left be x sub 0, which equals A. The next one would be x sub 1, x sub 2, x sub 3, x sub 4, and the last one in my example, B, is x sub 5. If I'm going to take an arbitrary number of rectangles, I could use n to describe the number of rectangles. In that case, B would be the nth one, x sub n. If I make them all the same width, which, as I've said, makes our job much easier, then I can compute the width of each one by taking the interval from A to B and dividing by the number of rectangles. In general, this gives us the expression B minus A divided by n. Again, technically, they do not need to be the same length, but it does make our job easier. We call this partitioning the interval A to B on the independent axis. Let's talk about what a regular partition is. When all the widths are the same, in other words, they draw better than I do, and they made all of their rectangles the same width, we call that a regular partition. If it's not the case that all the widths are equal, we simply call it a partition, but not a regular one. Regular means the widths are all the same. In that case, we can compute the width and call it delta x by computing b minus a divided by n, as you see here. The set of points for k equal 1 to or 0 to n becomes a equal to x naught. And again, we often say not, but it's not an NOT or a KNOT. This is actually x naught, which actually represents 0. Naught is an old-fashioned way of saying 0. If you graduated in the class of 1906, you would have said you graduated in the class of 06 or 06, where they dropped the N at the beginning. We no longer use that. We tend to say 06 instead of 06. When we're looking at these, notice that the left endpoint is the first one, and the last one is the B, the right endpoint of the interval. This divides it into n regions. We have n plus 1 numbers. We have the 0th, 1st, 2nd, 3rd, 4th, 5th, up to the nth, which gives us n plus 1 x values. But it divides it into n regions. Let's look at the picture again to see how this works. Notice we had an x naught, x1, x2, x3, x4, x5, which is 6 different x values. But when you look at the regions, there are only 5. When we do this, we call this a partition, and we're going to take some value in each little small partition, in each subinterval, say between x1 and x2, and we're going to find the value and compute the height of the rectangle at that point. We can write the kth point as the left endpoint A plus delta x times k, letting k start at 0 and go to n. That means the first time, don't add a delta x, so that x naught becomes a. Then x1 becomes a plus 1 delta x, the width of one interval, and x2 becomes a plus 2 delta x's, 2 over. We can take the height of that rectangle at some arbitrary point in the kth subinterval. We tend to call this the point x sub k star, and we use an asterisk for the star. The height is given by the function value at that point, f of x sub k star. Let's take a look at a picture so that we can see what we're looking at. If I were looking at the kth interval on this one, let's say this is the kth subinterval, I'm going to compute an x sub k star. The height there at that point would be the function value, and I would compute the height of the rectangle at that point. In this particular picture, notice that x sub k star actually corresponds with the left endpoint. In each partition, I've taken the left endpoint of the subinterval, found the height of the function at that point, and used it for the height of my rectangle. This is using the left endpoints and becomes called a left Riemann sum, again named for Bernhard Riemann, who created these. In the picture on the right, you can see that instead of using the height of the function at the left endpoint, this one is instead using the height of the function at the right endpoint of each small partition. You can tell, based on these two functions, that the left endpoint approximation is an underestimation, since it's missing some area that should be included as being under the curve. The one to the right is an overestimation because it includes some area that should not be included. We also have what's called a midpoint Riemann sum, which the textbook covers later in the calculus sequence, but I think it makes sense to talk about it here. Plus, it's one of the best approximations that we have, and I'd like to get it early. When we talk about the midpoint, we're actually subdividing the intervals, and we're taking the middle of the subinterval to compute the height of the rectangle. The first subinterval here goes from here to here, meaning the first box is the one now outlined in blue. And the second box is this one. Notice that they are using the middle of each subinterval to compute the height of the box. This is a better approximation because you can see that on each subinterval, it underestimates a little bit and overestimates a little bit, which sort of averages out some of the error. There is still error, but the midpoint does a better job of sort of averaging it out and is a much better approximation for most functions than the left Riemann sum or the right Riemann sum. By repeating this, we get an approximation for the area under the curve between x equal to a and x equal to b. We can take any point in the subinterval to compute the height, but it is customary and it's easier mathematically to use the left endpoint or the right endpoint or the midpoint. Let's now define what a Riemann sum is. A Riemann sum is exactly what we just discussed, using either the left endpoint, the right endpoint, or the midpoint of each subinterval, each partition, to compute the height of the rectangle. The formal definition is suppose the function is defined on the closed interval from a to b, which is divided into n subintervals of equal length, meaning we're doing a regular partition. Delta x given by b minus a, width of the interval, divided by the number of boxes that we want. If we take any arbitrary point, x sub k star, in the kth subinterval between x sub k minus 1 and x sub k, then we can compute the value of the area under the curve by approximating it with the sum of f of x sub k star times the width of the partition, delta x, summing from 1 to n. F of x sub k star is the height of the rectangle. Delta x is its width. This gives us height of the box times width of the box, which gives us the area of each box. And then we add all the areas together. Notice that delta x is a constant, and it does not depend upon the index of summation, which here is k. That means as a constant, we can factor it out. And since it's a regular partition where delta x is always the same, we can multiply that by the sum of all the function values that represent the heights of our rectangles. This is a Riemann sum. A left Riemann sum always uses the left endpoint. This formula here, x sub k star equal to a plus k minus 1 times delta x, will generate only the left endpoints. It will not give you the last one at B because it is not a left endpoint of any subinterval. The right Riemann sum, you can use the formula x sub k star equal to A, the left endpoint of the interval, plus k delta x. This will generate only the right endpoints of each subinterval. It will not generate the first one, x naught equal to A, because it is not the right side of any rectangle. The midpoint Riemann sum uses the formula where you add half of delta x onto the left side. This gives us A plus k minus a half of delta x, which gives us the left side plus a half more, or the right side minus a half, whichever way you want to think of it. In this case, we're using the midpoint as the height of our rectangles. In general, that midpoint approximation can be quite accurate. Let's take a look at increasing and decreasing functions and see how that affects the error involved in our approximations. If the function is increasing from left to right, notice that the left Riemann sum is an underestimation since it's leaving out part of the area under the curve. The right endpoint approximation, the right Riemann sum, is overestimating the area because it's including some area that is actually above the function. The midpoint, again, sort of averages out the area on each subinterval by including a little above and a little below. For a decreasing function, the situation is reversed. For a function that decreases from left to right, the left Riemann sum overestimates, right Riemann sum underestimates. And again, the midpoint Riemann sum, well, it sort of averages out the area, the error. Hopefully this explains to you why the midpoint is probably the best approximation, because it sort of averages out that error that's involved in computing the area. You'll learn two additional methods in Calculus 2, the trapezoidal rule and Simpson's rule. Even there, however, the midpoint Riemann sum is still often the best approximation. There are a lot of online sum calculators that you can use. I've put on here some of my favorites from Desmos and GeoGebra and indicated what they do. This first one will give you the left sum as well as the area between two curves. And the one below it gives you just the left sum, meaning the left Riemann sum. The right Riemann sum is given by this one here on Desmos. And there are some that give the midpoint as well. There are other Riemann sum calculators that will compute all three, the left, the right, or the midpoint Riemann sum. I have one in Desmos and two in GeoGebra. One of the ones in GeoGebra also will compute the trapezoidal rule and Simpson's rule, which you'll not learn until Calculus 2. Let's talk just a second about how to do a Riemann sum on a graphing calculator. On the newer graphing calculators, they have the summation symbol listed under the math menu. It's often choice 0. In that case, you can use the cursor keys after entering that sum in order to enter the lower and upper limits of summation and the summand, the expression behind the symbol. You can use the variable x for the index of summation. If you have a much older graphing calculator, you can still do the operation depending on how old it is. On some of these, what you'll do is you will instead, on the oldest type, hit the second button, then stat to get what's called a list. Then you move the cursor 2 to the right to highlight the word math. The menu will change as you move to the right. Scroll down to option 5, which is sum, and enter, or you can simply press the number 5. Then your screen will have sum with an opening parentheses. You have to go back into the list command by hitting second and stat again. Then move the cursor just 1 to the right to get the ops menu for operations. Again, option 5 is the one we want for a sequence command, SEQ. Now your screen should show sum, open parentheses, sequence, open parentheses. Then you're going to enter the expression behind the sigma symbol. In other words, the summand. Use the variable key for the index. You should now see something like this. Next, unbelievably, but in fact, you have to tell the calculator what the variable is. Enter a comma and then press the variable X button. Then another comma to indicate the lower index or lower limit of summation. I put in a 1. Then you enter the number of the upper limit of summation, and I entered 20. If you hit enter at this point, it will assume that you are adding 1 to the index each time, that you're iterating by 1. It does have the option to iterate by a different value by entering it after the upper limit of summation, following a comma. For the example I did, you will get 440. There are some other graphing calculators whose age is somewhere between the oldest and the newest. And on those graphing calculators, you may end up with an expression, right? It will ask you for the variable. It will ask you for the expression, which is the summand. It will ask for the lower limit of summation, the upper limit of summation, and your iteration value, which for us is always 1. And then you'll hit enter. Most of the time, you can use something like Desmos, where it's much simpler. You simply type into the slot the word sum, and it will automatically change to the summation symbol. It will always use n for the index of summation, and you can represent it by moving or clicking around. Let's take a look now at example 6, where we want to compute a left Riemann sum for the function x squared plus 3x by hand over the interval from 3 to 5 using 4 rectangles. I'm telling you that the true value is 232 thirds, or 77.3 repeating. In this case, I gave a link to something that will help you to find the values, and I gave you a link to the left Riemann sum of this when it's completed. Let's go ahead and talk about how to do this one, first by doing it by hand. When we're looking at this one, we need to first divide the interval between 3 and 5 into 4 rectangles. Now that I'm looking at this one, I'm wondering if I gave you the actual right value. I have the wrong function, or the right function and the wrong interval. Rats. Okay. I'll have to fix that in the notes. What I've actually computed, I believe, is the sum from 1 to 5. Let's change our 3 to a 1. When I'm looking at this one, what I want to do then is I want to divide from a equal x naught equal 1 up to b equal x sub n equal to 5. I want to divide it into 4 equal rectangles So my delta x is given by b minus a divided by the number of rectangles, which in my case is 5 minus 1 divided by 4, which gives me 1, which is why I want to change it from 3 to 5 to 1 to 5. Now what I need to do is compute the value of every left endpoint. It's going to be relatively easy here. X sub 0 is going to be 1. X sub 1 is 2. X sub 3 is 3. And x sub 4 is 4. Notice I do not use the last one because I'm doing a left Riemann sum. Now, in order to find an approximation for the area under the curve using rectangles, I'm going to use the height at the left point to draw rectangles. I'm approximating the area under the curve from 1 to 5 with the approximation of the yellow shaded area in the rectangles. To do this, I need to compute the area of each individual box. In this case, I need to know what f of 1 is, f of 2, f of 3, and f of 4. F of 1, in this case, is going to give me 4. F of 2 gives me 18, or 10. Which one am I looking at? F of 2 gives me 10. F of 3 gives me 18. And f of 4 gives me 28. Right. When I compute the values, what I end up with is f of 1 equal to 4, f of 2 is 10, f of 3 is 18, and f of 4 is 28. These are the heights of the rectangles. To get the area of each rectangle, I need to multiply by the width, which is 1. In this case, I'm finding the Riemann sum, which is going from k equal 1 to 4 of f of x sub k star, which is my left endpoint, times delta x, which is 1. This gives me the sum of 4 plus 10 plus 18 plus 28, which turns out to be 60. It's not such a great approximation. Again, because I've left out a lot of area. Notice it is underestimating because it's an increasing function. Let's look at the left Riemann sum. In this picture, you can see the left Riemann sum. And again, the only thing you want to change if you use this applet is the function, the number of rectangles, the left endpoint of your interval, and the right endpoint of your interval. The information in the second through the fifth slot. Leave the rest of it untouched. When I look at this, I can see down here in the sixth slot that it's giving me the estimation that we got of 60. Notice that if I increase the number of rectangles, it will get closer to the true value of 77.3 repeating. I can do that by grabbing on to the N in the slider bar and moving it to the right. Don't change the values of the interval, or you'll be looking at a different function. As I increase it, you can see that I'm getting closer and closer to the value of 77.3 repeating. You can also click inside the particular one to change it back to the number of boxes that you want. Let's now look at the same problem, but let's do a right Riemann sum. Next, after that, we'll do a midpoint Riemann sum. Go ahead and pause the video to work out the same function over the same interval from 1 to 5, but using instead the right Riemann sum, and then the midpoint. Let's now look at our right Riemann sum. Using only 4 boxes over the interval from 1 to 5, the width stays the same at delta x equal to 1. Notice that we are overestimating because it is an increasing function, and we're using the right endpoint for the height of the box. This gives us an estimation of 96, which we know is too much since it's exactly 77.3 repeating. Again, we can take a look at the right Riemann sum on Desmos using an applet. On this applet, again, you only want to change the function, the value of the left endpoint, right endpoint, and the number of boxes. We see here that it's giving us 96. When we look at this, notice that if we increase the number of boxes, we can get it to be much closer to the true value. In this case, as I increase, it rapidly comes down closer to 77.3 repeating. But even with 200 boxes, I'm still off. Let's now look at the midpoint. The midpoint Riemann sum, again, the width of the boxes is the same. It's going to be the width of the interval, 5 minus 1, divided by the number of boxes, 4. All that changes is the location where we compute the height of the box. In this case, we're going to use the middle of each of the partitions, 1.5, 2.5, 3.5, and 4.5. Since the width of each box is 1, that gives us the sum of each of those values, which ends up being 6.75, etc., giving us an estimated area under the curve of 77, which is pretty darn good for only 4 rectangles. It's very close. Let's now take a look at the midpoint Riemann sum in Desmos. Again, we only affect the values at the top, and you can see that it's giving us the value of 77. Now we're going to increase the number of boxes, but slowly, to see how long it takes us to get much closer to 77.3 repeating. 10 boxes, I'm at 77.28. And at 15, I'm at 77.309. When I get to 23, I'm at 77.32. And by the time I get to 44, I'm at 77.33, which has 100th place of accuracy. You may be wondering how I computed the values that I used for those. What I did was I graphed the function only over the interval from 1 to 5. And then I created a table and I computed all the values over the interval, including the midpoints. And I simply took the y values from the table to use in my examples in the video. We've already discussed how increasing the number of boxes can get our approximation closer to the true value. You can look at this one, which is approximating a cubic function with a wiggle in it. And as we increase from 4 boxes, then to 8, then 16, then 32, the value of the approximation gets much closer to the true value. And you can tell that the rectangles are much more closely following the shape of the function. The true value under this one over this interval is 6.75. And 32 rectangles got us a value of 6.7489, which rounds, of course, to 6.75. We're going to repeat this process by taking the limit as the number of boxes goes to infinity. It makes sense that if we could have infinitely many boxes, over that closed interval, we could find the true value of the area under the curve. In other words, if we took the limit of the Riemann sum, we should get the actual true value of the area. When we're doing this and taking the limit as the number of rectangles goes to infinity, the width of each rectangle is approaching 0. So it's often written in two separate ways that are equivalent. The limit as the number of rectangles goes to infinity of the Riemann sum, or the limit as the width of the boxes goes to 0 of the Riemann sum. In both cases, the delta acts as a constant that could be taken out of the summation. The proof of this is really beyond what we want to do. It's beyond the scope of this course. This is something you get to as a junior mathematics major when you study real analysis. What you learn in that course is that, in fact, it doesn't need to be a regular partition. All the widths can be different as long as the widest one, called the mesh, goes to 0 as you take the limit. In other words, all the widths have to approach 0. When you do that, you'll find that the limit of the Riemann sum gives you exactly the area under the curve. This ends our discussion of the Riemann sum, which of course is the birthplace of the definite integral. We'll learn in the next section what the definite integral is. And in the following section, we'll unite the indefinite integral and the definite integral when we discuss the fundamental theorem of calculus. I'll see you soon.